Groffman came up with the topic of snow is good, seemed horribly inappropriate. But you know, times change, and here we are. Vicki Kelly told me we got 53 inches cumulative reported snow out on at the environmental monitoring station. So you know, that's got to put up. We're headed to New York City even. So in that sense, I think we're probably setting some records. I should have said I'm Bill Schlesinger, president of the Cary Institute. Let me welcome you to the first of the 2011 Friday night speaker series here. That time when we either have our own scientists or scientists and others of note from around the country come and do their best job in translating and transmitting the state of science to a public audience on various topics in climate and winter, and what snow means is, of course, highly appropriate there. We've got some upcoming events that I want to alert you to. For the hardy among you, February 27th, we're going to have a winter walk on the Cary grounds at 2 o'clock. Details to be found on our website. I don't know if snowshoes will be provided, but we'll try to man it down or something so that it's walkable. On March 11, I think it is. March 11th at 7 p.m. we have a talk here. One of our co-sponsored talks with the American Bookstore with the topic of Moby Duck. Donovan Palm will be speaking. This is, I think, will be a lot of fun. A few years ago, a container ship full of rubber duckies made in China came upon a bad time in the Pacific, and it came to pass that the duckies spilled. And while 28,000 duckies may sound like a really bad plastic in the ocean type of pollution, they did allow oceanographers to do some really fascinating studies on the currents of the Pacific and where ducks went and where they ended up. And he's put this together into a popular book and will tell us a little bit about it. I'm hoping also in late February, although details are not completely finalized yet, that we may have a talk in here on methane in local water supplies derived from Marcellus shale hydrofracking. This is something we're working on. A lot of details that have to be worked out on that one yet, but that could happen in late February. But the two I want to alert you of are the walk on the 27th of February and Moby Duck on the 11th of March. So, tonight's speaker is no stranger to many people in Millbrook. He's been here far longer than I have, Peter Groffman, and is one of our senior scientists on the staff of the Institute here. Peter, the nut doesn't fall apart from the tree. He grew up in New Jersey, went to the University of Virginia for his undergraduate degree, University of Georgia for his graduate work. He did a stint at Michigan State as a postdoc, another stint at the University of Rhode Island as a faculty member, then saw the light, saw the opportunities of moving here, and did so a number of years ago, like 25 or something, and maybe, well, 18, okay, well, and has been enormously successful in a number of programs of research and such at the Cary Institute. Peter describes himself as a microbial ecologist and microbial biogeochemist, both of which should focus your attention. And he works on the little things in the soil and the sediments, things that make an enormous difference to the functioning of the world every day in terms of the quality of our soils, the quality of certain gases in the air we breathe, and are kind of microbes as kind of the unsung heroes of ecosystems. But he's made it his business to study them both here and at Hubbard Brook in New Hampshire and in the Baltimore urban ecosystem study. And through the course of some of his work here and in Hubbard Brook, he's come to appreciate snow and what snow means. And of course, snow is timely, both because of the way it is tonight, but because a warmer world of the future may have less of it, and in both time, shorter winter seasons, and in depth in terms of how it accumulates, and we need to have an appreciation for what that might mean for each of us. So without further ado, snow is good. Peter Groffman.
It's not our fault. I mean, we planned this program back in July, and as the week has gone on, I've become increasingly uneasy. And I was expecting people with these big icicles or snowballs. So I have a supply of snowballs here. So I will fire back if you So, but I see that people are not armed, and so I wanted to reiterate Bill's welcome. We are extremely glad you're here. These Friday night programs, we think have been a great success. We have all these people coming to talk science with us here at the Cary Institute on a Friday night. It's a great pleasure for us. And I'm going to try and make, one of the points I'm going to try and make tonight is that this type of interaction is extremely important for the progress of science and for the progress of environmental decision making. So that's going to be one of the themes. So welcome, we're very glad you're here. So my topic is snow is good. It seemed like a simple enough topic back in July. I think it's an uphill, we're going to be a little bit uphill today. So what am I going to hope to do? I'm going to hope to do a couple of things. I'm going to spend some time talking about, pushing this thing. Okay, I'll talk a little bit about how the climate is changing in the winter, and I'm going to make the case that the climate is changing in the winter in some surprising ways, and it has some very interesting and surprising effects. And I'm going to talk a little bit about how we study the ecological effects of winter climate change. So one of the great opportunities of these forums is we get to share a little science with you. And so we talk about how do we do science, how do we come to conclusions, how do we share those conclusions with people. So I'm going to share a little science with you, how we do experiments, how we interpret our data, and then spend some time about communicating results about climate change and these results. And again, it's something that we struggle with, and it's a great opportunity to share it with you. Okay, so how is the climate changing in the winter? Well, we know that the temperature is rising, and at least in the northeast United States, precipitation is rising. So over the last 100 years or so, it's definitely getting warmer, and it's definitely getting wetter. And that's very well known. What's less well known is that the temperature is rising more in the winter than it is in the summer. And the temperature is rising, and the precipitation is rising more in the winter than in the summer. And that's surprising, because when we think about climate change, we think about really hot days, and we think about hurricanes, but in actual fact, and I'll show some data to back this up, the temperature and precipitation are increasing more in the winter than in the summer. And that's kind of interesting, but it's not super exciting. What's really interesting is the most marked change in our climate is that we're losing the very cold days. So it hasn't been, and I'll show some data, it hasn't been minus 25 here in Millbrook since 1994. And the real big climate change that we've had is we've lost those really, really cold days. And something even more surprising is we haven't gained the really hot days. One of the things we were really worried about was that it was going to be 110 or 120 every couple of years. We haven't seen that. We've lost the very cold days, and there are some interesting effects from losing the very cold days. Some of those are good, some of those are bad. We see more winter rain instead of snow. So now, I guess there are various points where you can just boom, right? Actually, I had a question for everyone. Who's tired of the snow? How many people are like really tired of the snow? See, not that many. And how many people think all the snow is great? Yeah. See, I had a sneaking suspicion that this was a group, and it's just an incredible challenge because the kid in all of us is just so excited about all the snow until we have to go to work and get out the driving. So I knew that this was going to be a good group, and most people were just going to be extremely happy that it's snowing. In most years, and we'll show some data on this, we have more rain instead of snow. We have less snow cover, the snow season. We're going to talk about seasonal changes in our snow season. The days of snow cover are less, the depth of the snow pack is less, and the snow season is changing. The ice season on our lakes is changing. And then the real topic that I've been most interested in, and I will talk about quite a bit today, is the idea that our soils are frozen. So this is surprising. When we lose the snow is a blanket. Warms the soil, and when we lose the snow, somewhat surprisingly, we have colder soils and more frozen soils. And one of our research papers is called Colder Soils in a Warmer World, and that's what we're going to talk about quite a bit today. Okay, so some data to support these statements. As Bill mentioned, I do a lot of work at the Hubbard Brook Experimental Forest. It's a long-term ecological research site in New Hampshire. Gene Likens founded ecological research there back in the 60s. The United States Forest Service has been collecting climate data there since the mid-50s. And not surprisingly, the temperature has been going up. And at Hubbard Brook, we measure the temperature down at the bottom of the hill, where it's warmer than it is up at the top of the hill. But both at the top of the hill and the bottom of the hill, the temperature is going up. And there's nothing really surprising about that. Although, it shows, these trends are you see there's a lot of variability, and the trends, while they're significant, are not super strong trends. And one of the real themes in climate change is the weather keeps interfering with the climate. The long-term changes are changes in climate, but the weather, what we have every day, is what we perceive every day. It's much harder to perceive these rather subtle changes than it is to perceive the change in climate. And that's going to be a theme through a lot of what we talk about tonight. Now, we also have long-term monitoring here at the Cary Institute, run by Vicki Kelly, who collects the data and then puts the data in an extremely usable format. And we again see interesting trends. So at the Cary Institute, starting in '87, the mean annual temperature has risen, and again you can see there's quite a bit of variability. And I think the best way to look at these data, and this is the way Vicki summed it up in the report, so 2010 was the 18th year in a row with a higher than average temperature. Right? So we have a long-term average temperature, and each year we say, well, was it warmer than average or was it colder than average? Well, 18 years in a row, the temperature has been above average. It's like the Lake Wobegon effect, where all the children are above average. Well, all our temperatures are above average, which means that it's getting warmer. And it's probably a more robust indicator of the fact that it's getting warmer than this trend line, which is very difficult to see. But I said, no one is surprised that the temperatures are going up. But what I mentioned before is that we've lost these really cold temperatures. So this is a graph showing the change in the frequency of temperature. This is at Hubbard Brook. And what you can see is minus 25 degrees is good and cold. And it hardly ever gets to minus 25 anymore. So you can see there's been a 40% decline in the frequency of minus 25 degree temperature. It means only about half as frequently does it get to minus 25. And you can see a lot of these low temperatures, there's been huge declines in the occurrence of low temperatures. And then again, surprisingly, here are high temperatures, and there have been small increases in these extremely high temperatures, but they're very small. And the much more marked effect is that we've lost the very cold temperatures. And these are the data at Hubbard Brook, and here are the data from Millbrook. So here, again, plotted what was the lowest temperature in each year in Millbrook. And you can see in 1994 it got to minus 27, and it hasn't been minus 27 since that time. Now, is this good or is this bad? What do we think? So, whose furnace was making funky noises the other night? Right? Got to minus 10, and the furnace is kind of going like this. And so, in many ways, the fact that we've lost the very low temperatures is good. Our furnaces don't break, there are human health, and people get sick, people die from a very cold temperature. So it's kind of hard to argue that it's a terrible thing that we don't have these extreme cold temperatures. But there are some surprising ecological effects from the loss of very cold temperatures. So the distribution of organisms, including some pests, are very strongly affected by very cold temperatures. So the hemlock woolly adelgid is an invasive insect that's killing all the hemlock trees in this part of the world. And the hemlock woolly adelgid it's not wiped out, but it certainly is hindered by minus 25 degrees. And so you can see the hemlock woolly adelgid is moving into this area right now. Many of our hemlock trees are afflicted with the adelgid. So in 1994, the adelgid took a hit, but of course it hasn't been that cold ever since, and so the adelgid is spreading, the infestation is getting worse, and all our hemlock trees are going to die because we don't have these very low temperatures anymore. So maybe we used to have minus 25 every 5 years or so, and it would be very hard for the adelgid to get established. But now that we've lost these very cold temperatures, we're much more susceptible to these invasions by invasive pests like the hemlock woolly adelgid. Now again, some of those organisms, very cold temperatures limit the distribution of organisms. So there are some organisms that we don't want, like the hemlock woolly adelgid or the tiger mosquito, which I've never seen. I don't want to see a tiger mosquito. But maybe we'll be able to grow bananas. Or more camellias. I've always wanted to grow camellias, and these really low temperatures will kill your camellias. But maybe if we lose them, we'll be able to grow some things that we couldn't grow. And indeed, the growing season is getting longer. So here's more data that Vicki Kelly put together from the environmental monitoring system. Here's the growing season. Okay, so how long is our growing season? Right? So the frost-free days, and it's been going up since the 80s. And so where maybe it was a 200-day season in 1988, it's up to 210 or 215 days now. And you can tell why the growing season is getting longer. So it could be because spring is coming earlier, or it could be because fall is lasting longer. And indeed, the change is much more in the fall than it is in the spring. So if you look at fall, fall used to start on the 250th day of the year, and now the first frost is maybe on the 260th or 270th day of the year. So our falls are lasting longer. And it's kind of unfortunate that spring is not coming earlier. Spring starts on day 100, and we're kind of still stuck with mud and slush, that kind of spring that we all enjoy so much. It wouldn't be such a bad thing if spring would come earlier. But the growing season is getting longer, and indeed, one day we'll be growing bananas here in Hudson Valley. Now, as long as we're talking about seasons, the ice season is changing. So a sensitive indicator of winter climate change is ice cover on lakes. And this is Mirror Lake, which is at Hubbard Brook. And Gene Likens, again, founded the work at Hubbard Brook, and he started measuring ice cover on the lake. He has a very specific method for determining when the lake has frozen over and then when the ice has melted. And the ice season on the lake has shrunk quite a bit. So here's the days of ice cover on Mirror Lake. Started off at about 150 days in 1966, and it's been going down, been going down, been going down. And again, you see these trends that are hard to see. So you get some cold years where there's ice on the lake for a long time. You get a bunch of years where there's really low amounts of ice. But the trend, the long-term trend, is down about half a day a year of ice cover on the lakes. It's a good integrated indicator that suggests that the climate is definitely changing in the winter, and it's going to have some surprising effects. So it has effects on the fish that live in the lake, and on the chemistry of the lake, and all the processes in the lake are affected by ice cover, and they are changing in a pretty dramatic way. Okay, snow. This is, again, we can have more booing here if you really want to boo about snow. So indeed, we have less snow. It's hard to imagine in this year, but this is data from Hubbard Brook, and the snow depth, the maximum snow depth at Hubbard Brook has been going down steadily. Again, this is starting in the 50s, going down to the current time. The amount of water in the snow, which is very important for water supply, has been going down. And the days of snow cover have been going down at Hubbard Brook. And again, these trends are very significant. And they're fairly relentless, but there's a lot of variability because we have weather. And in each year, the weather that we perceive on a day-to-day basis makes it very hard to perceive these trends. But the longer data record you have, the trends are quite significant. Now what's interesting is snowfall. The amount of snow has not gone down. But the snow cover and the snow depth have gone down because it's warmer. So it snows, maybe it snows not the same, but it's melting faster. And so we have less of a snow season. And we can see that in Millbrook. So here's the snow data in Millbrook, a much shorter record than from Hubbard Brook, but there's no trend. The amount of snowfall hasn't changed. Remember, we had a couple of big years of snow. Where are we now? We are about 130 centimeters here in this season so far. So we're not, it seems like there's been a lot of snow, but we're not, well, it all depends. If it keeps snowing, we may set a record over here, but certainly there's a lot of variability in the record, and the amount of snowfall hasn't changed much. Here's an interesting tidbit. New York City, the climate record is much longer, right? So they've been keeping climate data in New York since 1869. And of the top 10 snowstorms that have fallen in Central Park since 1869, 5 of them have been in the last 10 years. Now that's kind of amazing, right? Because one of the trends that we've been looking at hard in the climate is the idea that we're getting more big storms. That we're getting more rain, and we're getting more rain because we're getting these really big storms. And this kind of supports that 5 of the top 10 snowfalls over the past 142 years have been in the past decade. And so that's an interesting change. Snowfall, again, is a hard one. But again, we get a lot of snow, but we have less of a snow season because it's warmer and because we have more rain in the summer. So this is again from our data here. What proportion of the winter events are rain? And so maybe in the 80s it was 45% of them were rain. Now it's maybe 55% of the events are rain. So we're getting more rain and less snow in the winter, and that rain will melt the snow, and so the snow season is changing. These are subtle changes in snow. What we're particularly interested in, what I'm going to talk about quite a bit today, are these marked snow droughts, years where there's just no snow. So here's a picture from Hubbard Brook in February of 2006. There ought to be 30, 40, or 50 inches of snow on the ground. But here we are in February, and the ground is bare for the most part, and the soil is frozen like a rock. You can see the streams are frozen, and these events, these snow drought events, were what are the focus of our research, because we became concerned that these were really big stresses, big disturbances in the forest, and that they were occurring more frequently, and therefore we studied them, and I'll talk a little bit about how we studied them. Okay, so the climate's changing in the winter. It's changing in complex ways with a variety of effects. And one of the great challenges we face is how to sort out all those different changes and all those different effects. This is true in all aspects of science, and it's particularly true in environmental sciences. We have multiple effects. How do we sort them out? So a new idea that we have for sorting out multiple effects is focusing on something we call ecosystem services. And an ecosystem services, a simple definition of ecosystem services, is defined as things in nature that people value. And so we'll use the example of forests. There are many things that go on in the forest that we value. The production of wood, the production of water, the preservation of biodiversity. There are aesthetic and spiritual values of forests. And we can make a list of all those ecosystem services, of all those things that we value in the forest. And it's useful because it allows us to make a very comprehensive list of the things that we value and the things that might be threatened by any type of human activity or any type of environmental change. And even more importantly, if we can make this comprehensive list, we can use it as a platform for evaluating trade-offs and conflicts, which is what really plagues us in environmental science. We want to manage the forest for bird biodiversity, but we also want to manage the forest to produce firewood. How are we going to do those two things? How do we evaluate those trade-offs? It's a huge complication in environmental science. One idea is that focusing on ecosystem services is a way to do that. But we're not sure. This is kind of a controversial topic. There are some people who say, oh, we shouldn't talk about ecosystem services because people don't understand what that means and it doesn't help them. And then other people think it's quite useful. I'm excited to be talking with this group tonight. I'm going to lay out this work in an ecosystem services context, and I'll be very curious to get some feedback about, is this a useful way to look at multiple changes in nature. A little bit more about ecosystem services. So there's a group called the Millennium Ecosystem Assessment that has developed the ecosystem services concept quite a bit. And they split these ecosystem services up into three groups: provisioning services, regulating services, and cultural services. And these provisioning services are things that we know are important, things that we can quantify very easily, and things that we can put a dollar value on. So things like the production of wood, or the production of food, or the production of fuel, we can quantify that coming out of an ecosystem, and we can put a dollar value on it. We then have this group of regulating services, which are things we know that are important, things that we have a good quantitative understanding of, but we can't really put dollar values on them very easily. So we know that forests, for example, are very important in regulating the climate and in regulating floods and in purifying water. And we have a pretty good quantitative understanding of those things, but what's the dollar value of those? A little bit harder to do. And then this third group, these cultural services, are things like aesthetic values, spiritual values of forests, recreational values of ecosystems, things that we know are very important, but are very difficult to quantify and almost impossible to put a dollar value on. But these are the things that are really important. If you propose to cut down a sacred grove of trees somewhere, people are out in the street raising huge fuss about something like that, even though we can't put a dollar value on it. We can't quantify it as readily as we can quantify things like water purification or the production of water. And ecosystem services, we argue, is useful therefore, because it allows us to make this big, long list of services and then gives us a platform for evaluating trade-offs and determining what's most important and how can we manage for multiple objectives and achieve more of what we want. So let's apply this to forests. So forests are what we work at Hubbard Brook. Forests are what we study quite a bit here. What's our list of ecosystem services for the northern forest? We certainly are interested in the production of wood, and increasingly we're interested in managing forests to produce energy. Certainly we know we use our forests to produce clean water. Our reservoirs are located in forested watersheds. They produce quantity of water, they produce quality of water. They play a role in purifying a whole range of air pollutants. They cool the climate in the summer, they warm it in the winter. They pull carbon out of the atmosphere and combat the greenhouse effect. And then these cultural services related to the maintenance of biodiversity or aesthetics and recreation. Simple list, but I think useful because now we're thinking about forest ecosystems, and there's a lot that we're hoping to achieve from in these forest ecosystems. And then we then can say, well, what are the threats to these specific services? It also allows us to say that things are good or bad. So if I'm interested in managing a forest to get clean water, and I know that if there's a lot of snow in the forest, the water is clean, and then if I have less snow, I end up with water quality problems, I can then make statements such as snow is good. And again, it helps to focus our attention on what we're studying and what our outcomes are. Okay, so snow, let's go back to snow is good. And here's this picture I showed you earlier. We became very concerned that one of the real kind of surprising aspects of climate change was going to be an increase in these snow droughts, where you go out in February and the forest is bare and the soil is frozen, and this is going to be a real stress on the forest. And we set out to study this, and so we've been conducting research for about 10 years on the interaction between snow depth and soil freezing in the forest at Hubbard Brook. And this work has been funded by grants from the National Science Foundation. And the big idea here is that snow is important as an insulating blanket of the forest. And if you go to New Hampshire or you go to Vermont, in most years those soils never freeze. Soils that are typically snow-covered, they don't freeze in the winter. And they're unfrozen, and there's a low level of biological activity going on all through the course of the winter. Now, if you lose that insulating blanket, the soil freezes, and it's a huge stress on the forest. In particular, we're worried that it kills the roots of the trees, and it kills the microorganisms that live in the soil. And so then, I've got this big mass of dead roots and dead microbes that are decomposing. Almost like if you add compost to your garden, it decomposes and releases nutrients. And so the idea here is if we kill roots and we kill microbes, we're going to get this accelerated nutrient loss and this decomposition, and the nutrients are going to come washing out of the system and the roots are going to be damaged. And if you think about how can soil freezing damage roots, think about what it does to the roads or what it does to the sidewalk. That frost heaving is a huge physical stress, and the roots don't like it much. And again, we're quite concerned that, that climate change could increase the prevalence of these soil freezing episodes, and we see they occur now, and the idea is that they may be occurring more frequently. So how could we study this? So, and this is where I wanted to share with you a little bit about how we do science. So here's an observation we made, that here's a climate change that could be coming, it could be increasing, could have a big effect on the forest. So how do we go about studying it? Well, we shoveled the snow out of the woods. So we set up snow manipulation plots. And so this is a 30 feet by 30 feet plot where we removed the snow from these plots. We kept them snow-free through January. And we were trying to simulate the snow drought. Now, if you look at this picture, it doesn't look all that different than this picture. And so, at least visually, our plots are simulating, our experiment is simulating the phenomena we're trying to study. Now, what is it? Anyone have any thoughts about this? So I'm trying to get people to think scientifically. Here's a challenge. We need to study this phenomenon. What do you think about shoveling snow out of the woods as a way of studying this? What's that? Do you think that? So because the question is, and this is true in all aspects of science, right? So we need to study phenomenon, and we need to manipulate the systems to study them, and so we want the manipulations to be realistic. For example, this problem is not all that different than, let's say I invented a new artificial sweetener, and I wanted to know if the artificial sweetener was safe. Right, so now what I really would want to do is I'd want to give that artificial sweetener to 20,000 people over 30 years and see if a bunch of them got sick and died. But I can't do that. Right, so instead what do? I take a rat and I feed the rat a chunk of artificial sweetener the size of this podium and see what happens to that. And that's how it's done. And they are facing the same problem that we're facing. This is my rat. And the question is, what do we learn from rats? So, too small. And so I'm going to come back to this because it becomes very important in terms of how we make inferences. So, Liddy, what do you think?
Yeah, I would also wonder about if the soil is disturbed when you're shoveling.
Right.
Does that change?
So we had to go to great pains to make sure that we weren't destroying the soil when we shoved it. And actually what we did to do that is we actually we would leave an inch of snow on the soil surface and pack that down to protect the forest floor. So that's the kind of scientific thinking I'm hoping you get the group to do, because we did this experiment that was the first thing we worried about quite a bit. What else?
You're only changing snow cover. There may be other elements associated with a snow drought, such as changes in air temperature,
right.
Rainfall versus snowfall, things like those.
Right. So one of the real drawbacks of this is I'm definitely simulating less snow, but I'm not necessarily simulating warmer temperatures. And so in a couple of years we did these experiments, we had warm El Nino years, and it worked out well. Other years, when we simulated no snow with kind of a cold winter, it was not a great manipulation. I think this is fun scientific thinking. Okay, Alice?
So the airflow around it would be different than if the entire area were...
Right. And so indeed, this is a preliminary test plot where we have the snow kind of piled up around the side, and you're very much worried about that altering the airflow and the water flow around these plots as well. So we got a little more careful when we moved the snow.
What about the effect of sunlight?
Well, what I think is interesting. So when the soil is dark like this, it absorbs more energy, and so actually leaving the inch of snow on that we did increased the albedo and reflected the sunlight back, and actually helped create more of a freezing stress. So it helped us in that we got a freezing response, but maybe a little less realistic.
Well, one of the things you're doing there is creating an oasis for animals to come and feed in that specific area, and they could root around quite a bit.
Well, so we're going to come back to that. We're going to come back to snow manipulations and animals, some big ones, some big ugly ones.
Is the area big enough to interact with the other parts of the forest?
No way. And that's always the problem. Is how big are your plots in forest ecology studies? Not big enough. But we had to. These plots were not. So in order to do this, we had to snowmobile up about five miles in the woods. Then you had to hike about 30 minutes to the spot to shovel it out. And 2 people could shovel a 10 meter by 10 meter plot in about an hour. And if they were much bigger, then it became impossible to do. So the size of these plots is a source of great heartache in these. Okay, we're having fun, so I'm going to push this along, but we're going to come back to what we learned from these plots in a minute. Okay, so we did this manipulation, and it worked pretty well. And so we're measuring. We have continuous temperature measurements in these plots. So we're measuring. Here's the temperature in the soil at 10 centimeters, and so about 5 inches deep in the soil. And here we are in the fall, and the soil is not frozen in the fall. And then as we go into the winter, the temperature goes down, and here are the snow-covered plots, the reference plots, and you can see they never freeze. The snow is an insulating blanket, and the soil stays at about 1 degree centigrade. It's about 39, 40 degrees, like your refrigerator, and things are growing. I don't know about your refrigerator, but things are growing in my refrigerator. And then down here, these are the shovel plots, which you can see are colder and a lot more variability. It's like taking the insulation out of your attic, and it's colder, and it's a lot more variable. The soils are frozen, and you can see the manipulation created just the variation in conditions that we want. And the idea is, in a warmer world, the thermal regime in the soil is going to be quite a bit different if you lose that snow cover. And it had huge effects on the forest. So the first thing we saw is that it killed a lot of roots, and it doubled overwinter root mortality. Now there's a phrase to take home. So tree roots die. They're always dying, and they're always growing. And in the winter, you have in the winter it's tough for tree roots, and always a significant number of roots die in the winter. But in our treatment plots, twice as many roots died in the winter as in these reference plots. So in the reference plots, about 15% of the roots died over winter, and in the treatment plots, about 30% of the roots died in the winter. And we did this in 1 year, and we did it in another year again. And so as we predicted, soil freezing was a huge stress, killing the roots of the trees. Now now let's think about ecosystem services. This is going to have a negative effect on tree growth, the production of wood, the sustaining of biodiversity, productivity. Many services are linked to productivity, and if you kill the roots, you're going to have productivity problems. One of the other things that roots do is they take up nutrients from the soil. And in the plots that were treated, nutrients came pouring out the bottom of these sites. So we measure this thing called leaching, and we have these devices that capture the water that's moving through the soil. And that water is moving through the soil, and it's leaving the ecosystem. And when we treated these plots, we had huge increases in nitrate leaching. Nitrate is a form of nitrogen that plants really like. And so here we have our plots where they were frozen in the winter, and then the following summer, the nitrate came pouring out the bottom of those treated plots. Then again, the second year we had another frozen event, and then it came pouring out, especially in these maple plots. So we're losing nutrients. And again, the roots are dead, which is bad for the trees. One of the reasons it's bad is because they use the roots to take up nutrients, and so they can't take up nutrients. So there's, again, a productivity ecosystem service decline. And these nutrients, what they get into the water, they're water pollutants. They cause overgrowth of algae in lakes and streams and rivers. So now I've got a water quality problem as well, right? So the forest is hurting. I've got these nutrients pouring out of the system. So I have a water quality problem as well. And I see it with nitrogen, and I also see it with phosphorus, the same leaching effect. Here's the frozen soil. The next summer, phosphorus is pouring out of these maple plots. Again, the second year, I've got phosphorus. And phosphorus is of huge concern in lakes. If you get phosphorus into lakes, it causes overgrowth of algae, or eutrophication, they call it. And so I'm getting less snow, and everything's going to hell in the forest. The roots are dying, the nutrients are pouring out the bottom, I have productivity ecosystem service problems, I have water quality ecosystem problems, I even have air quality ecosystem problems. So we measure N2O, nitrous oxide. How many people here are familiar with nitrous oxide? Okay, so nitrous oxide is laughing gas, but it's no laughing matter in the atmosphere. It's a very potent greenhouse gas. And we have our plots. That are treated with this freeze treatment, and they're producing quite a bit more nitrous oxide than the reference plots. And so I've got a water quality problem. I've got an air quality problem. I have productivity problems in the forest. And I also have methane problems. One of the things that the soils do is they consume methane out of the atmosphere, and these treatment plots are consuming less methane. Again, another potent greenhouse gas. So you can see I've got a suite of problems that are coming out of these forests. I'm inhibiting the productivity of the forest. I'm hurting the water quality, the air quality. I'm excited about my results. And so I'm going to go to Washington, and I'm going to go to the Forest Service, or I'm going to go to the President, and I'm going to say, we've got a real problem with winter climate change and ecosystem services in forests. Okay, how do you know this, Professor? Well, I've got these little plots in the woods, and I've had some undergrads shoveling, and things are really changing. So I have that discussion in my head, and so then maybe I don't go to Washington to tell them about that. And then we come back to these plots, right? So the question is, and we all grapple with this. So we get scientific results, and do we believe them, or what's our level of certainty in our results? And so we did a lot of very good experiments with these small plots, but we were concerned that, and as you all did an excellent job of pointing out what the potential strengths and weaknesses of the small plot studies are. So one thing that's very common in all science and in environmental science is we take another approach. So another approach is to exploit natural elevation gradients as natural climate change experiments. So here's a picture of Hubbard Brook. And at Hubbard Brook, I've got about 1,500 feet of elevation. And the trees and the soils are about the same. So as you go from the low parts of Hubbard Brook to the high parts, it's pretty much similar forest trees and similar soils, but the temperature varies quite a bit. It's quite a bit warmer down here than it is up here, about a 2 degrees centigrade difference. And so one idea is, instead of shoveling and doing that manipulation, I can locate plots of any size that I want down here, and I can compare them with plots of any size that I want up here, and use this as a natural experiment. Okay, what do people think about this as a way of doing these experiments? Is this better or worse? What are the strengths and weaknesses of this? Yeah.
I was wondering where the timberline would fall.
The timberline falls someplace in Colorado. So think about in New England, we do get above timberline if you get to like Mount Washington, up around 5,000 or 6,000 feet. But here at Hubbard Brook, the highest it gets is around 2,400 feet. And so it starts as northern hardwood forest here, and it's still northern hardwood forest here. If it gets a little higher in elevation, you get spruce fir, and if it gets much higher, then you get to the timberline. So this is a narrow elevation range.
What side of the mountain do you look at?
Well,
North, west?
so what I like to contrast is the south-facing low elevation plots, which are the tropical regions of Hubbard Brook, with high elevation north-facing plots, which would be the polar regions. And as long as, when we laid out these plots, and we've done some experiments, and our current research is focused on this, we try and get south-facing low elevation and contrast it with high elevation north-facing to maximize the climate difference. And that works, except what's the great possible flaw in these studies?
Amount of light.
Light would vary, that would be one thing. Yeah? Well, temperature, right, so temperature and moisture is what we want to vary. So we're definitely exploiting the temperature difference, and we do get a moisture difference as well. And that's okay. But if but there's one great danger in all gradient studies.
The ecosystems are different.
Right. So how do we know? So I told you that the soils and the plants are about the same at low elevation and high elevation. But the review panel is going to say, how do you know that everything's the same? And that is the problem with all gradient studies. Gradient studies are used very commonly in ecology, and we agonize over, are we controlling, we would like to vary just one thing. We'd like to vary the climate, but we need to hold everything else constant, which you can never do. And so, and I illustrate this because in many ways this is a much better approach than the small plots, but it has strengths and it has weaknesses, just like the small plots have strengths and weaknesses. And in science, whether it's biomedical science or whether it's environmental science, we need to apply multiple lines of evidence and multiple types of experiments before we can come to some type of conclusion. And we hope that everything shows the same thing. So I got some results from those small plots. What do we get from the elevation studies? About the same. So, and these are our ongoing studies, but the manipulation works. So we go out and we indeed see that the elevation gradient gives us differences in soil freezing. So it starts to snow in the White Mountains in November and December. And if we go out there early in December, and actually it's not we, it's the students and technicians that do this work, I never go out. But if one went out at this time, you would find that these high elevation plots have snow. Early in the season, at high elevation, there's snow, and the soil is not frozen. But at low elevation, just a couple hundred meters down the slope, there's no snow, and the soil is freezing. And if you establish this difference at the beginning of the season, it persists the whole season long. So as you go out way into January, still these are the colder plots. I mean, they're high elevation, colder plots, but they have more snow, and so they're warmer. And so this whole idea of, do we get colder soils in a warmer world? Well, we might if we lose the snow. And so again, here, there's less snow, and so the soils are colder. And so the elevation gradients have shown us about the same thing that the plots have, and it's greatly increased our confidence that winter climate change is very important in controlling ecosystem services in these forests. The other thing that's nice about the elevation gradients is it allows us to do summer as well. You mentioned moisture content is going to differ, and indeed, the high elevation plots are always wetter in the summer. And so now we get to do both winter and summer climate change with the elevation studies. And I'll report on that sometime else. Yes?
Can you explain what the difference in UV radiation and different options?
Well, that's a really good question. We haven't measured it. And UV radiation is an extraordinarily hot topic in ecology right now because it facilitates decomposition of plant litter. We used to think that was a completely biological process, and there's actually a huge abiotic component going on with that. But we haven't measured it, so that's a good thing to measure. Okay, so now I did two kinds of studies, and now I'm really confident that I'm getting changes in winter biogeochemistry associated with winter climate change, and I'm ready to take this to the public. But shocking to me, the public is not all that excited about changes in nitrogen biogeochemistry. And it's a big disappointment to me, but Bill and I have learned to live with that. But what was interesting, when we started doing these experiments in the woods and studying the winter, we attracted other people who were interested in other changes that were going on in the woods in the winter. One of the most interesting changes that was a better platform for engaging people in was moose. Okay, so one of the big changes in the northern forest over the last couple of decades has been an increase in the number of moose. So especially in New Hampshire, moose populations have really gone up quite a bit. And moose have a huge impact on forests. Moose can eat a lot. Right? So people, right, everyone has had a deer eat your garden. How about who's had a moose? I mean, it is really completely, they really are big. And I don't think they're all that attractive either. But. Okay, so the moose are changing, and this attracted the attention of Lynn Christensen, who was doing her dissertation research. Lynn is now a professor at Vassar College, and began an interest to study the effects of moose on the forest. And the thing that attracted Lynn, we were talking about changes in snow, and the impact of moose on the forest is very strongly controlled by snow. So if you think about it, moose are, in the winter, are browsing. They're eating the little buds on the little plants. And if the snow is deep, then the plants are protected. And so if you have a lot of snow, then the little plants are protected. And if you have less snow, then the moose impact on the forest is potentially much, 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 much bigger. And Lynn cast this in a multiple stress context. So you have these poor trees are getting hammered from below and from above. If you have less snow, the soil is freezing, and so their roots are frozen. And then you've got these big honking moose eating them on the top because they're not covered up by snow anymore. And the multiple stress, and the concern was that if you give them this double stress where you freeze the soil and you intensify browsing, would this push certain types of ecosystems kind of over the edge into the ecological abyss? So things like balsam fir, which is a boreal species, which we're concerned about. We may lose it from the northern forest because the climate's getting warmer. We may indeed lose balsam fir, but probably less just because it's getting warmer, but more because of this multiple stress, where you have a stress from below and you have a stress from above. And we found this was actually a better way to engage, get people thinking about winter climate change, because I think almost everyone relates to multiple stress. Hammered from below, hammered from above, and it was very interesting in terms of the way these science programs grow. And you start with one line of evidence and you attract other people, and then you learn new interesting things about how it goes. Okay, so in summary, we've done a body of research that suggests that winter climate change is really important for our forests. We are losing snow, and it gives us declines, marked declines in a series of ecosystem services that we care about. Water quality, the production of the forest, these greenhouse gases which affect air quality, biodiversity, aesthetics, recreation. There's just a suite of ecosystem services that are affected by winter climate change, and most of these are mediated by this loss of snow which causes the soil to freeze, and then there's this cascading series of effects caused by the loss in snow. And our confidence in these results is growing as we do multiple experiments, using multiple different approaches. And I think it's a good example of how science develops, and then gives us confidence that we can then go to society and say, here are some results that you should consider taking action if we want to combat these losses of ecosystem services. And I think it's an open and shut case. Okay. So the last thing I wanted to talk about was, okay, so now I've got these results, and I believe my results, and I'm very interested in the interface between science and society. So I do these experiments. I would like to get society to understand these results and use them in some useful way. And I think we can't have any discussion of climate change without talking about the controversy around climate change. So there's big problems with the perception of people's perception of climate change, and it's really inhibiting society's ability to take action to combat it. And there are just a few things that I'm going to talk about. One, it's a politicized issue. Science should not be politicized. It's almost as if I started to think that gravity, there's a vast right-wing conspiracy that is trying to pull me down. It's not. Science issues should not be politicized. So we're going to talk about how this is politicized and how perhaps we can get out of that. We have had some deliberate obfuscation and sowing of confusion. We have pretty good evidence that climate change is caused by burning fossil fuels. There's lots of money to be made selling fossil fuels, and so legitimately, the people who sell fossil fuels have a great interest in sowing confusion and uncertainty about climate change, and it greatly inhibits the ability of the public to perceive and take action about climate change. We'll talk about that a little bit. Scientists are to blame. Scientists sometimes are good communicators. Oftentimes, the number one thing that the scientists communicate is, I'm a lot smarter than you, and that doesn't help. And we've seen examples where scientific communication has inhibited the flow of information from science to society, and we're spending a lot of time thinking about how we can improve our communication skills to help the public to perceive and take action with climate change. And then, fundamentally, climate change is just a difficult thing to perceive. The weather is always interfering with our ability to assess climate change. So again, I'm trying to convince you that things are changing a lot in the winter, and there's less snow, and it's having an effect on the forest, and you're going to walk outside, and you're going to, it's going to be hard. And so there is an inherent problem with climate change, and it's very difficult to perceive long, gradual changes when we're constantly affected by the weather. So let's talk about some of these things. The politicization of this is just a huge problem. And here are some slides that were given to us by Matt Nisbet, who's a professor of communications at American University. He was here for a conference, and this is an amazing and depressing graph. So they polled people and they said, do you think that changes in the Earth's temperature are caused by human activity or by natural changes? And 75% of Democrats thought that it was caused by human activities, and 40% of Republicans thought. Now, the factors. Well, they also have it by split out by college grads and not college grads. But I would argue, I think it's whether the climate is changing due to human activity is not affected by political orientation. And so the truth is clearly somewhere in between. And the fact that people's perceptions are affected by the political orientation is a huge failure of science communication. And we're never going to be able to come to any consensus about what to do about climate change until we close that down. And to me, that's a big problem for us to deal with. And I think that scientists have a huge role to play. So, Matt Nisbet also tells us that science is held in very high regard by society. Most people, 70 or 85%, think that scientific research is a useful thing. And people trust scientists. And so on climate change and other issues, Americans believe that scientists hold greater expertise, are less self-interested, and should have a greater say in decisions than industry leaders, elected officials, and or religious leaders. Now this is good news for scientists because it means that we have a role to play in closing this gap. And so, how are we going to do that? And so the question is, here's an opportunity for science to really have an effect on society. How can we do it? And so we had a conference here about a year and a half ago on science communication, on facilitating the flow of information from science to society, and we called it Restarting the Conversation, and how we can re-engage with, how scientists can re-engage with society in more effective ways. And I wanted to end with this because one of the clear recommendations that comes out of communication research is what we're doing right now is what we should be doing. And there's been lots of research on how people get information, and one of the recommendations was if we would like people to engage with science, we need to have ongoing conversations between scientists and groups of people in settings like this, town meetings or science cafes or science festivals or using blogs for electronic communication. Getting people to come and engage with science, to learn a little bit about how science is done, about how we draw conclusions, to look at the data together. The idea is that can really build scientific understanding, and then people can come to their unbiased or objective decisions about scientific information and then decide what they're going to do about it. And we have the data to do it. I tried to highlight the long-term monitoring data that we collect here at the Cary Institute. I think has a huge role to play in helping local people to understand, is the climate changing, what are the effects on the environment, and should we do something about it? And we know that newspapers are not as popular as they were. Support for science reporting is not what it was. And so there's this idea that academic institutions like the Cary Institute should be involved in these local, regional, digital news communities. Go to our website and you'll see our environmental monitoring data, and you'll see an interpretive report that very clearly says what is and what isn't changing about the climate. And we're very excited to develop forums like this and expand these, and that's considered to be a state-of-the-art approach in science communication. We need feedback, though. So we've learned that scientists oftentimes are very good at telling people what they think they ought to know. And what we've learned, that rather than lecturing or hectoring the audience about what I think you ought to know, the idea is we ought to think more about our audience, and we ought to think about expressing our results in frames of reference that are more relevant to the way people think. So when we think about climate change, some people are very interested in the effects of climate change on public health. Other people are concerned about the economic effects of things like sea level rise or economic opportunities associated with green jobs. Or many people feel that there's a religious and moral duty to protect the environment and we shouldn't disturb it. These are very important frames of reference that maybe scientists aren't all that comfortable with, but if we engage with audiences like this, we can come to understand those frames of reference and have a much better dialogue. We can restart the conversation between science and society. And this forum is an example of that, and so I thank you for coming, and I hope you keep coming back. Thank you.
Sure, we can lean on Peter to take a few questions.
I'm sure you're aware that Senator Inhofe has filed legal action against several climate scientists in this country. You're aware of that?
Yes.
Do you have a position on that?
I think as a citizen of the government, and the government has funded our scientific research, Senator Inhofe has every right to question our science, and we have an obligation to share that with him.
But he's calling it fraud.
Right. And if he wants to call it fraud, and again, as an elected official of the government, he's allowed to investigate if it's fraud, and it's not. And I think that investigation should be open. And I think that it should really be publicized, because the data on climate change is really quite good. It's going to have to be a very ambitious fraud. And because people have been measuring the temperature, lots of places, and there would have to be a really there's no way. And so he has a right as an elected official or as a citizen to question science. We have an obligation to discuss our data with him. And I would welcome it, because the science behind it is really quite strong. And if he has legitimate concerns, then that's a fine thing. If he's deliberately trying to obscure or obfuscate, then that's not so good.
He's trying to pull funding.
Right. And if he wants to investigate that, to pull the funding because the science wasn't sound, he won't get very far, because it's pretty sound science. Yeah.
The scientific method starts with theory, then collects data, analyzes it, and either proves or adjusts the theory and goes out and gathers data again. And what the gentleman was saying, I think is really important. For all of society, it seems to us that some people limit their intake and start with the theory and seek data to confirm it and reject. They call it, I forget what Research County calls it, mainstream media and so on. They reject all sources that don't confirm their theory. So you've got people that believe in science and other people that believe in confirming what they start with. And how do you bring this back together?
I mean, I think that is one of the great things about science is it's a shared open experience. So I showed you how I did my experiments, and I wrote a paper in a scientific journal that describes that in excruciating detail. People are having trouble sleeping at night. I have copies of this. And why do we do that? So that someone can then go out and duplicate my experiment. So and people actually have done these experiments in many places. They duplicate the experiments, and sometimes the results are the same, and sometimes they're a little different. And that's what's great about science. It's a shared, open process where we all get to share the results. But it's only one way of knowing. Right? So many people have other ways of knowing things. They use their gut feelings, or they use spiritual feelings, and that's a different way of knowing than science. But science, it's an open process, and so we have scientific results, and people can test them and pose other theories and test those, and that's how it goes forward. And it has to be an open process, which I think is what's great.
One of the problems I see with science has to do with Godel, and that is the difference between proof and truth.
Between say that?
Proof and truth.
Proof and truth.
When it's a resuming logical system of understanding requires certain axioms that you can't prove
Right.
to be proved.
Right.
And so it's possible that those axioms are not, but some things are not true.
So science is an ongoing process, because we have very few laws in science, right? So we have the first law, right, of thermodynamics, you can't win. Second law, you can't even break even. But and that's in thermodynamics. But it is true. Things you don't write things down as a law because they can always be overturned if our conceptual understanding changes. And the roots of science, of climate change science, go back. So when was Arrhenius? This is covered in Bill's book, which I recommend highly.
1896.
Okay, so Arrhenius in 1896, he said, he kind of reasoned about the greenhouse effects. It said the Earth should be a lot colder than it is, but because there's carbon dioxide in the atmosphere, well, the Earth is a lot warmer. So he had an observation, kind of a basic science theory, And he also kind of scratched his head as he was watching the peat fire in his little Swedish house burn. He said, if I keep putting more carbon dioxide in the atmosphere, what's going to happen? Is the Earth going to get really warm? And that was based on pure theoretical reasoning. And then people tested that idea. Was it true or was it not true? And then we've gone on from there.
Would it be easier to move the snow like you did in that rat example, or to move the animals? Because I had a case in my family where my mother didn't like tree frogs at night, so she asked my brothers to move the frogs from one pond to another. But which would be easier, to move the pond or the snow, or to move the animals?
Well, so with animals, the way you do it is you do it with exclusions. So to study the moose, one way to study the moose is you put up fences around to keep moose out. And we do that here at the Cary Institute. Ray Winchcombe leads these experiments on deer exclosures. And so you put up a fence and you have an exclosure, and so then you get to see how you can evaluate the effect of the animal by doing an exclosure. And it's the same with snow. So we did snow removals or snow exclosures. The other way would be to add snow. And the way they do that in other places is you put a fence up. This works in tundra or in grasslands where there's less trees. You put a fence up, and the wind blows, and the snow piles up on one side of the fence, and there's less snow on the other side of the fence. And so you do both, and ideally that is a very good test of your ideas, because you make some predictions about what happens if you remove the snow or the animal, and you make some predictions about what happens if you add the snow or the animal. It's another way to do it. Yes?
The impression I get as a reader of newspapers and journals and so forth is that you are presenting the weight of authority of the scientific community, which of course we value. On the other side of the coin is, say, the Sarah Palin of the world. But surely there are some in the scientific community who disagree with you, even though it's a small percentage. I know it's maybe hard for you, but can you make it? What is the case that they would make, so that we can understand the other side of the scientific community that may disagree with the authoritative way? What do they say?
It's difficult to understand. The way science works is it is very difficult to prove or to determine absolute truth. You have weight of evidence. And the weight of evidence in climate change is very, very high. And I'll give an example of smoking. Okay, as an example, right? So we had evidence starting in the 60s that smoking was real bad for you. But there was a lot of money to be made selling tobacco. And so as late as 1990, you could bring in scientists to Congress to say that the link between smoking and lung cancer is not that strong. As late as 1990. Those scientists were wrong. And there was a huge weight of evidence saying smoking is a problem, and then you could always find a few scientists say no. They were focusing on, well, the evidence is not that certain. There are always skeptics in any scientific endeavor. I had a professor who didn't believe in continental drift. Right? You know how the continents move around? He had a bumper sticker on his door that said, "Stop continental drift." So there are always outliers, but we have to go to the body of evidence. And so if it's 1,000 to 3, then we have to say that there's a body of evidence, and there are skeptics, and they're focusing on the variability, or they're focusing on some novel interpretation of the data that's not supported by anyone else.
Smoke for cancer causes smoke.
I was reminded of this because the King's Speech, so that movie, The King's Speech, there was a bit in there where one of these doctors was recommending that he smoke. Smoking is good for your health, and it reminded us. And so now it seems completely inconceivable to us that people ever questioned the link between smoking and disease. But it was not so clear in 1960. By 1970, it was real clear. By 1980, there was no joke. But still, by 1990, there were still people saying we need to teach the controversy, and there's uncertainty about these things. And over time, you sort these things out. And I think, in 10 or 20 years, we won't be questioned. There won't be as many people questioning climate.
Peter, many thanks. And I hope to see you all again at one of our upcoming lectures. And many thanks for coming out on a snowy night tonight to enjoy this evening with us.
It is really great for you guys to come out.
I have no clue. got here a little bit late. Just a little before you. I got your message.
Oh, did you? Oh,
Yeah.
I'm going to share something.
Huh?
Share something.
With who? Yeah, I am too.